toss your phone up in the air. Newton says it's going to come down. Safe, predictable, normal. Classical physics is the part of reality that we turn to for clarity. If you follow the math, there's usually a definitive answer. Now, imagine if sometimes the phone doesn't come down, or sometimes it doesn't stay up, or sometimes it moves to the left, and it just randomly decides to go wherever it wants. That's the strange reality of quantum mechanics. But quantum mechanics is awesome, by the way, because it doesn't simply break the rules. It completely shatters our understanding of reality itself. Nobel laureate Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Even Einstein himself got theological about the concept, saying, and I quote, "God does not play dice with the universe." But unlike philosophical paradoxes, quantum paradoxes are actually baked into the universe, and each one is more terrifying than the last. Now, among these strange ideas, there's one concept that you can never shake off when discussing quantum physics, and that's the concept of superposition. It's the idea that something can exist in multiple states at once up until it's observed. It sounds fictional because in our everyday world that is literally impossible. Superposition once gave physicists sleepless nights until Erwin Schrödinger broke it down with a famous measurement problem. You may be more familiar with it under the name Schrödinger's cat. The quantum world deals with tiny particles like electrons, for example. Because of superposition, an electron can be in spin up and spin down at the same time until you look at it, and that is the coolest thing. And then you can suddenly know for sure what position it was. What Schrödinger did with superposition was expose just how ridiculous sounding it truly is. So we'll use his example. Imagine a sealed box with a cat inside of it, and along with the cat there's also a tiny radioactive atom. If the atom decays, a poison is released. If the atom doesn't decay, nothing happens. Whether or not this atom decays is a quantum event. So here's the paradox. Quantum mechanics states the atom in question is both decayed and not decayed. Considering the fact that the atom contains a poison, its state determines whether or not the cat is alive. But that's the heart of the problem. Before you open the box, it feels like the cat is both alive and not alive. It's the sort of idea that tears a hole through reality in sci-fi stories. Now, ironically enough, this was Schrödinger's point. He was trying to show us something with this measurement problem. Yes, it's an interesting thought experiment to think of the cat in both states, but his core argument was that quantum rules do not make any sense when applied to everyday objects. Schrödinger's cat is essentially a mockery of naive interpretations of the quantum realm. And when you think of the quantum world, it's crucial to avoid fitting it into a box of conventional expectations and logic. True understanding comes from embracing quantum mechanics as its own thing, its own kind of weird. Now, Schrödinger's cat is just the warm-up. It's pointing to an even stranger outcome. If reality only becomes definite from our observation, then what is making the decision for the definite things that we see? Is it us? Is it some measuring device? Or is there something pulling the strings that we can't perceive? Now, Einstein noticed this problem and he did search for answers. Here's what he found. Two quantum particles created in a single shared quantum state. For ease, let's call them particle A and particle B. Now, the pair are entangled together in a way that links their properties. Generally, quantum particles tend to have distinct properties like mass, spin, and charge. These two particles are then allowed to fly light years apart, so much that they basically don't even exist within the same area in space. To make it simpler, imagine two coins with the ability to act inversely of each other. So you flip one coin and it lands on heads. Well, by that logic, the other must be tails. And no matter how far apart those coins get, Say I have one of the coins with me in Toronto, while the other is in Australia. Then my coin flip will inevitably correlate with the coin flip in Australia and vice versa. Now, these quantum particles are linked, even when they are light years apart. So, if particle A is measured to have spin up, then particle B must instantly have spin down with the same applying and vice versa. Now, we're building on this. Remember what we said about superposition and observation. Before we measure particle A, it's in superposition, so we don't know for sure if it's spinning up or down. But if we observe it to have a spin up, we can conclude that particle B has spin down. And this conclusion is thanks to the way that their properties are linked. But Einstein, and I adore this, called this spooky action at a distance. For a scientist at his level, there were certain foundational truths driving the completion of a theory. The two classical principles he held on to were locality and reality. Locality means that an object can only be influenced by its immediate surroundings. Put simply, nothing can travel faster than the speed of light. Next is reality, where the physical properties of an object exist when they are not being observed. So, why did all of this bother someone who could arguably be called the smartest man to ever live? Well, let's look at it this way. If I were measuring particle A in this room, and my cousin Steve in Australia is measuring particle B, we'd know each other's coin states based on the correlations that our particles have. So even if Steve was light years away in Andromeda, once I observe heads on particle A here on Earth, particle B all the way out there is guaranteed to have tails. And that's how it works for the pair's particular entangled setup. This spooky action implies that the measurement that I made instantly influenced particle B no matter the distance. And that was problematic to Einstein's principle on locality because it's unquestionable. Particle A correlated with particle B instantly, even while they were light years apart. To understand it better, 1 light year is about 9 trillion kilometers. This interaction is unfathomable to a rational mind. Currently, this level of correlation is not usable for communication, so nobody can actually send information faster than light. Yet, the weirdness endures. 3 physicists, Einstein, Podolsky, and Rosen, drew a conclusion to the problem. Essentially, they believed the spooky action to be impossible, arguing that the only way to avoid it is if the particles already had their definitive spin values determined from the beginning. These predetermined values were called local hidden variables, but the 3 couldn't actually prove the existence of these local hidden variables. They weren't claiming to know what these variables were, only that there was a gap in the logic. And that gap is terrifying. A quantum paradox that's essentially sealed away by science's greatest minds. If you were to explain Einstein's point of view to a 6th grader, it almost feels like Einstein closed the gates of an unknown realm. Without a concrete answer, engaging with it risked something far greater than what Einstein was ready to accept. So, for nearly 30 years, Einstein, Podolsky, and Rosen's point of view remained a philosophical debate dubbed the EPR Paradox. Enter John Bell, the man that transformed this paradox into a mathematical inequality called Bell's theorem. Bell realized a distinction between the predictions made by quantum mechanics and the predictions of any theory that satisfied Einstein's principles of locality and reality. The main distinction was quantitative. So he created a complex set of measurements to perform on particle A and particle B, turning Einstein's complaint into a testable equation, like a mathematically intense game of truth or dare. And here's what it boils down to. If Einstein's local hidden variables were correct, the measurement correlations between both particles could not exceed a certain mathematical limit, and he called this the Bell inequality. On the other hand, if quantum mechanics was correct, the correlations would exceed this limit. The conclusion proved that Einstein was looking at it the wrong way. Now, that doesn't mean he was completely incorrect. It's just that the quantum world is non-local. So it's like he was applying basketball rules to a game of soccer. In the literal sense, quantum mechanics predicts these strong correlations as an accurate description of the universe. But for us to truly understand it, we must sacrifice those ideas of locality and reality. That leaves the spooky action as a very real thing. And now, interestingly enough, even though the particles are correlated, there's really nothing that shows us how this can transmit useful information faster than light. The EPR problem and Bell's theorem further drive home the idea that the quantum world doesn't play by our universe's rules, but they do both seem to draw on a final observation. Right now, it might feel like you understand quantum mechanics a tiny bit better. The concept is a lot like buying a Labubu doll. You never know which one you're going to get in each mystery box, that's what I'm trying to say here. But you can still measure probabilities. But what if I told you that sometimes, depending on the Labubu you get, you can retroactively change the past? To really grasp what I'm saying, let's take a look at a famous piece of foundational physics, the double slit experiment. Let's get nerdy with this. So imagine a wall with two parallel cracks in it. Let's say you have a gun that shoots out single photons of light. Photons are they're not a wave, they're not a particle, but we'll call them particles of light for ease. When you begin firing the tiny particles at this wall, you expect to see two distinct lines shining brightly behind the cracks. But that doesn't happen. Instead, you find a shimmering interference pattern with many bright and dim stripes. This is the signature appearance of a wave, meaning that each particle isn't just taking one path. Instead, it's going through both slits at once, which a particle can't do. And as those possibilities interfere with each other, a pattern is created. That's when you decide to put a detector at the slits. Now, this detector measures which path the photon bullets took. So, you fire up the experiment again, and you fire that gun. But this time around, something strange happens. The interference pattern at the back of the slit vanishes. Instead, the particles behave like you would conventionally expect, creating two distinct bands of light directly behind the cracks. I love that. This experiment establishes a rule with quantum mechanics, and that rule is, when observing, you can either see the wave behavior and the interference, or you can get the path information, but never both at the same time. It's like getting the information causes a collapse in the wave function. The particle feels aware of an observer. I just want to repeat that for how mind-boggling it is. The particle knows you are looking at it, so its behavior changes from the stage fright. It's wild. Now, I want to pause it here. It's not literal awareness, though. It's not looking at you and having thoughts like we would. The wave-like possibilities actually collapse into a definitive outcome. It's like the act of checking freezes it into a single choice. Reality feels solid until you start paying attention to the things happening just outside your field of view. The system's watching, sorting, and shaping your life without ever announcing themselves. It's strange how much of our world is influenced by forces that we never directly see. And once you realize how easily the smallest traces of your life can be captured and used against you, the whole picture starts to feel unstable. Which brings us to something very real, very present, and very much worth paying attention to. Your name. Your income, your family, even your personal struggles. Data brokers collect these fragments of your life and package them into lists that are then sold to the highest bidder. Some of these lists have some genuinely disturbing labels like tough start, young single parents, and rural, and barely making it. These are categories that target the most vulnerable in our society. We're all being sorted into boxes that predatory companies and bad actors can use to identify and exploit us. This is one of the biggest tragedies of the modern algorithmic systems that we all live under. They're invasive and they're dangerous. Incogni was built to fight back. Incogni automatically removes your personal information from the places that you can't see. Data brokers, people search sites, predatory directories, all the hidden corners of the internet where your identity is quietly being traded for profit. Doing this yourself would take weeks or even months, but Incogni handles it automatically and continuously, keeping your data out of the hands of bad actors. And with their new custom removals feature, you can take it even further. Just Google yourself, find a site exposing your information, copy the link, and Incogni's privacy experts will work to have it removed, even from sites outside their automated network. Your data should not be their currency. It should be yours, so take it back. Go to incogni.com/aperture deal and use the code ApertureDeal to get 60% off an annual plan and keep your information out of the hands of people who want to harm you. Because they can't harm you if they can't find you. Now, back to our story. Now, looking changes reality in the present, but you have to wonder, has anyone ever tried to look after the fact? Like you'll come to learn along the way. Someone has in fact asked most of these burning questions in quantum physics. In this case, we have something called the quantum eraser paradox. Instead of firing single photons, what if an advanced setup generated pairs of entangled photons, just like we observed in the earlier EPR problem? Let's just call them photon A and photon B. Photon A plays the role of the signal photon. It's the brave mercenary that we're sending towards those double slits. Meanwhile, photon B is the idler photon. This is the one we use to get the answer on which path photon A actually took. Now, we have a special device at the slits to give photon A a barcode, depending on which slit it went through. Because photon A got the barcode, photon B also inherits knowledge of this barcode thanks to the pair's entanglement. Then photon B flies off to a distant area for detection, carrying the secret of which path photon A took. So, here's one of the possible results. Because of the information available to photon B, photon A acts like a particle and the screen shows two distinct bands. In other words, no interference. This result is the same as the double slit experiment. The interference pattern is destroyed by observation. Now, another possibility is what I would like to call the eraser. So, let's take a look back at photon B after it flew off into the distance. As an experiment, it's sent through a quantum eraser that destroys any possibility of ever knowing which slit photon A took. If you're not sure why anyone would want to do that or care, stick with me, we'll get to it. Here's where things get interesting. When taking another look at photon A after scrambling photon B, something strange happens. Its data is correlated with what is erased on photon B. In other words, an interference pattern magically reappears. It's like it undoes the result of being observed. Because photons B information got scrambled, photon A starts to behave like a wave. And if you're not going right now, let's run it back again for some more clarity. Photon A hits the screen and does the conventional double slit observation. We record the journey, get the data, and we know with certainty that it ended its journey as a particle. Now, erasing the barcode doesn't rewrite photon A's past. It only reshuffles the data. Yet, from the way it appears, it's as though photon A has already recorded past changes because of what is happening with photon B. It's like watching a detective show. When the big reveal happens, you realize that the clues that you ignored earlier suddenly change how you interpreted the case. Quantum mechanics can behave in ways that are eerily similar. So, what does this tell us about time? Is it the linear journey that we believe in? From the quantum eraser, it feels like changing the present can influence the past, which is creepy but also very fun to think about. And it's not entirely far-fetched. Today, episodes of shows that aired decades ago are edited quietly to fit a new vision. A politically incorrect joke is quietly phased out. And sure, that fits with the times, but if we jump at every opportunity to cover up a messy past, what kind of future are we shaping? Maybe reality and fiction don't truly exist within distinct lines. Most times, We doubt the realities observed by others, like when your friend barges into your college dorm room claiming that a test was graded. To you, it might sound unbelievable, especially when the grades are out before the scheduled time. Meanwhile, if your friend is coming from the professor's office, they've just observed a different reality. Now, both are technically true, yet there's one objective truth in play. The quantum world has something that invokes the same sentiment, but this time things are so fantastically, fascinatingly paradoxical. This time, let's bring back my cousin Steve from Australia. So Steve gets into a sealed lab and performs an experiment to measure the spin of a particle. Remember that in quantum mechanics, particles are usually in superposition. So prior to measurement, it seems like a particle is up and down at the same time. Steve performs the measurement and he finds the particle is up. Acknowledging this, he writes it down in a note. Meanwhile, I'm outside the lab. While Steve carries out his experiment with the quantum particle, there's something that I, where I am, can't seem to grasp. You see, Steve, the particle, the measuring device he's using, and the notebook are now part of a single quantum state. Furthermore, from my point of view, the sealed lab and everything within is in a state of superposition. This state will persist until I open the door to the lab and perform my own observation. So, where exactly does this collapse into superposition actually happen? More importantly, why does it happen? I know that Steve must have recorded a result, but the superposition still remains as long as I haven't made my measurement. Fundamentally, we tend to assume that there's a definite boundary between the microscopic quantum world and our conventional classical world, yet they exist together. This isn't just philosophy. The 2025 Nobel Prize in Physics bridged the gap even further. It was awarded for experiments proving something that we once thought impossible. Quantum particles can actually pass through energy barriers, even in circuits that are large enough to see. The paradox of Steve and I is known as Wigner's friend, proposed by Eugene Wigner in 1961. It's one of the more direct confrontations with the nature of quantum measurement. The Wigner's friend paradox is like watching the same show with your friend, then meeting up the next day to compare your notes. But during the meeting, you both realize your endings were totally different. Both of you are convinced that what you watched was the real ending, and until you compare the notes, nobody really knows the objective truth. That's one of the ways quantum mechanics is dead tricky to observe. However, with a little switch in perspective, you can actually gain some helpful benefits from its strangeness. Take the quantum Zeno effect, for example. You know how observation makes a wave turn into a particle? Well, what if you just kept observing a quantum system constantly, making sure it never evolves into anything? It sounds random and frankly unnecessary, but there are scenarios where this could stabilize fragile quantum systems. In quantum computers, this kind of use case is a lifesaver. For example, what if there was a radioactive atom in an unstable quantum system? If left untouched, the atom would decay, and the effects of its radioactive properties could destroy that system. However, when you decide to frequently measure its state, like, say, every microsecond, that atom's evolution would be slowed so significantly that it couldn't get the chance to decay. It's like having a boiling pot that stops boiling when it's watched. The crazy part is that this has been experimentally verified in reality. When you engage with quantum physics, it's almost like there's a whole new world out there to mold. Sure, quantum mechanics has weird, mind-boggling rules, and yes, absolutely. But in the grand scheme of existence, humans have always found ways to tame that weirdness. 400,000 years ago, the cavemen that discovered fire were probably in awe at the strange element dancing before them. Today, fire is a fundamental part of the human experience. I don't think we think about that much. In contrast, quantum mechanics were only discovered in the mid-1920s. Yet, we are already starting to find ways that it can help us as a species. That burning quest for knowledge could take us beyond the stars one day. Speaking of useful functions for quantum physics, let's find a bomb. Yep, And not just that, we'll get to find this bomb without touching it or even setting it off. The idea is that with quantum science, it's actually possible to obtain information about the presence of an object due to the absence of a certain interaction. It's a deduction on a very bizarre level. We'll use a device called the interferometer. This interferometer relies entirely on a single particle's wave nature to operate. For our example, we'll be looking at a photon's wave nature. Now, let's go inside the interferometer. Within, we see that a photon is fired at a crossroads called a beam splitter. At this quantum crossroads, the photon doesn't just choose one path, instead it acts like a ghost, splitting and traveling down both paths at once. That's superposition. To take things further, the two initial paths meet again at a second crossroads, directing the photon to one of two final sensors. We'll call these final sensors detector D and detector C. There are two possibilities at play from here. First, if there's no bomb, both ghostly versions of the photon travel their paths. Remember that it is in superposition. They meet back at the second crossroads. Here, they interfere with each other, like two waves overlapping in an ocean. Since they are perfectly tuned, they cancel each other out at detector C and reinforce each other at detector D. A perfect wave interference, meaning no bomb. When there's a live bomb on the path, it acts as a detective. So, if we are looking for a live bomb in a sea of dud bombs, we place an interferometer. Then, as the photon is traveling, the moment it encounters a bomb, it chooses one of two paths. Remember how quantum particles do that thing where they stop the superposition when there's an observer? Well, that's what we're taking advantage of. Now the particle has two paths in front of it. If the bomb blocks one path, the interference pattern collapses. Sometimes detector C clicks, and that can only happen if the path was blocked by the bomb. That means we would have successfully detected a live bomb without setting it off. In this second path, because the bomb forced a choice, only one path's worth of the photon arrives at the final crossroads. Remember that perfect wave interference that we mentioned? That's broken, because one part of the wave did make it to the end. Without the interference, the rules of the final crossroads change. Now the photon can either go to detector C or detector D. Detector C never lights up if the bomb is absent. So if we run the experiment, read the waves from the ghostly versions of the photon, we can infer two things. First, the bomb didn't explode. But if the interference breaks, then a live bomb must have been present to break it in the first place. Therefore, we found the bomb without ever touching it. There is one small problem. Using this method to check for a bomb, there is always going to be a 50% chance the bomb actually does go off. It's like the photon can choose where it goes, and we have no power to influence it. However, if it chooses the path without the explosion, it's still a higher chance of detecting a bomb without setting it off. This truly impressive feat is revolutionary, and here's a simpler version of this. It's a lot like finding out whether or not someone broke into your family home. Normally, when you ring the doorbell, your dog barks. This time, you ring the bell and your dog stays silent. Well, that doesn't mean you saw an intruder, but the lack of a specific action, like a bark, implies that something is wrong. When there's no information, we can sometimes learn more than we think. But what happens when we have a confirmed theory that says all information is erased? Can we still recover that information using quantum means? Well, as you might have guessed at this point, quantum mechanics claims that yes, in fact, we can. Bringing things back to Einstein will highlight his take on black holes. In the theory of general relativity, Einstein described a black hole as a region of space-time where the gravity is so intense that nothing, and keyword here, nothing, not even light, can escape once it crosses the event horizon. Black holes are quite simple. They possess three classical properties: the mass, angular momentum, and electrical charge. No one can escape. Nothing can escape once it falls into a black hole. Every form of matter remains, whether that's a person, a book, or a hard drive. All the complex information within matter seems to get irreversibly crushed and swallowed, leaving only three classical properties of the black hole. According to Einstein's general relativity, the information is effectively destroyed. Therefore, the past history of what fell in is completely irrelevant. Well, the quantum world says otherwise. Quantum mechanics works on a principle that information must always be conserved. It's like once something exists, its previous and future states are confirmed to also exist. Even if you burn a book, the quantum world says the book's existence doesn't cease, and you can actually confirm that the ashes before you were once part of a book. So if you know the current quantum state of a system, there's a possibility that you could calculate its entire past and future. You see how that messes with general relativity? According to the quantum rules, information in the matter that fell into a black hole must still exist somewhere, and it can't just vanish. And it sounds plausible, especially given all we've learned already about quantum physics. But, as always, there is one small problem. How can anyone prove this to be the case? Well, that's where physicist Stephen Hawking comes in. In the 1970s, he discovered Hawking radiation, a concept that marries general relativity with quantum mechanics. At the edge of a black hole's event horizon, quantum fluctuations constantly produce pairs of interesting virtual particles dubbed a particle and an antiparticle. Usually, these pairs instantly annihilate each other. However, near the event horizon, one particle may fall into the black hole, while its partner escapes as Hawking radiation. The escaping particle actually carries positive energy away from the black hole. Meanwhile, the falling particle carries negative energy into the black hole. If you wait for the black hole to lose mass and shrink for trillions of years, you can start waiting now, I'll pause you there, something cool happens. Once the black hole evaporates, it leaves only thermal Hawking radiation in its wake, like steam rising off a hot surface. As useless as thermal radiation might seem, that's where the paradoxical implications actually begin. Say your hard drive fell into the black hole. Two things would have happened to its quantum information at this point. It's either destroyed with the information vanishing, or it's preserved, somehow escaping via the random Hawking radiation. Now, if the information is truly destroyed, it violates the fundamental laws of quantum mechanics. That makes it paradoxical because the laws of quantum mechanics are undeniably true. On the other hand, though, preservation means that the Hawking radiation isn't truly random, but rather it has the complete quantum state of everything that has ever fallen in. Why is that a problem? Well, according to scientists, it challenges our current understanding of gravity. Finding a solution to this paradox demands a theory of quantum gravity, one that smoothly merges quantum mechanics and general relativity. And right now, doesn't exist. Quantum mechanics feels like it turns everything inside out and then upside down. With this black hole information paradox, there's no denying that quantum physics feel like a cheat code to the classical physics and its laws. But the problem is that cheating is a lot harder than actually finding answers that we can fit into our current reality. If you could always guarantee a win, would you choose to keep winning no matter what? Even if it meant that a version of you loses in every other reality? Let's picture a game of Russian roulette. This game is extra special because your gun is connected to the quantum world. Now, normally, quantum events feel like pure chance. Either an atom is decaying or it's not. The only way to truly confirm something is when it collapses into one result or the other. It's similar to a coin landing on heads or tails. The many worlds interpretation proposes something slightly different. It says that the coin actually never stops spinning. Instead, the universe splits. Yep. And it is going to get weirder, I promise. In this interpretation, when an atom is measured, reality divides itself into multiple paths. We have one universe where the atom doesn't decay, in another, the atom decays. Both outcomes are equally real and happening, but they happen in separate, parallel worlds that are completely cut off from each other and cannot communicate. It's admittedly a stretch to imagine this being the case, but it works as a test to stretch the boundaries of what quantum mechanics can achieve. To take things even further, let's go back to that quantum gun we talked about. So, you're sitting in a room with this weapon. The trigger is connected to a quantum device. If you pull it, the atom within can either decay or not decay. If the atom decays, the gun fires a lethal shot. If not, the gun just clicks, and you're good. You're determined to pull it 100 times in a row. No matter who or what the gun is pointed at, something unnerving will always happen. Now, if there's a friend watching you on a monitor, there are 2 points of view at play. The normal point of view is that your friend sees the bullet go off about 50% of the time, watching in grim resolve the horror of it all. After all, the odds of 100 trigger pulls being non-lethal are impossible, right? However, if your friend is watching in the many worlds view, they see the universe split with every pull. After the first pull, the friend sees 2 universes. After 100 pulls, they are now looking at trillions of possible universes. In the vast, overwhelming majority of them, the gun went off. But let's go back to your perspective with the special gun. In the many worlds view, you only ever experience the pulls where the gun doesn't go off, because those are the ones that you survive and continue to perceive. Your consciousness can only keep existing in branches where the gun never went off. I think that's obvious. So each time you pull the trigger, 2 things happen. Branch A, the gun fires. Your experience in that branch suddenly and violently ends. In branch B, that gun doesn't fire. Instead, you hear a click and you live, and you continue to experience. Every time you pull the trigger in this many worlds view, reality splits, and from your point of view, the gun is always clicking. Subjectively, you experience 100 times where the gun does not go off. But in reality, there are trillions of timelines where it did, and, well, tough luck. This quantum immortality twist tells us that in the many worlds view, your conscious awareness is like a ghost that automatically shuffles into one of the rare universes where you continue to exist. This isn't necessarily a recipe for immortality. Let's just check you at the gate there. But when you think about it deeply, it evokes this bizarre feeling. By this logic, everyone alive would only be here at the cost of trillions of universes where they're not. Every moment where you hesitate to cross the street, every time you stepped in front of a car, countless other versions of you met a much different fate. Quantum physics shows us that reality is far, far stranger than our everyday experience reveals. From Schrodinger's cat to the many worlds interpretation, the universe isn't a concept that we can fully grasp in a classroom. The truth is much more complicated than we let on. Things can exist in multiple states at once, and observation itself can actually shape reality. Now, here's the fascinating part. Despite its strangeness, quantum mechanics isn't just abstract. It's the foundation of the world that we live in. The device in your pocket, every bit of modern technology, are all part of what pushes humanity forward. These weird, counterintuitive rules may scramble our minds, sure, but they are still fundamentally a part of our life. And by embracing that strangeness, we have the key to understanding the universe and ourselves.